All right, so as the clock turns 1 o'clock, we're going to start our class today. So this is the 6th lecture out of the 8-lecture series, our QIS 302. And this class is on superconducting qubit fabrication. And it's our pleasure to have Suhas Ganjam to give us this presentation. And Suhas is from Yale University, works in the lab of Professor Rob Shokov. Yeah, so just a reminder to everyone, please feel free to type in your questions in the Q&A panel, and I will try my best to keep track of the questions and have them answered either in text or in live session with Suhas. Okay, so let's go ahead. The stage is yours. Suhas, yeah.
All right. Thanks, Chen. Hi, everyone. Today I'll be giving the lecture on superconducting qubit fabrication. Yeah, let's get right into it. So why is qubit fab important? Well, in general, coherence is going to be dependent on many things like your circuit design, your fridge wiring, your fridge setup and filtering. But the coherence of our superconducting qubits is very highly entangled with our fabrication. So the materials that we use, the fabrications that we employ really do matter. And if you want to optimize everything, it's going to take a lot of work and a lot of resources. But in a research environment, it's important to have a process that's reliable and simple enough that anyone can do. So I hope in this lecture that I can communicate some of the basic fabrication processes that are involved in qubit fab. In particular, I'll go over the basics of metal deposition, lithography, and patterning, and give you a general overview of how to fabricate a superconducting qubit. Importantly, the specific details of each process, like the recipes and the SOPs, will be very specific to the equipment and resources that you have available. So as a result, if your lab has never done qubit fab before, there will be some process development that needs to be done along the way, like tuning deposition parameters or etch recipes or exposure doses, etc. Okay, so let's talk about the anatomy of a qubit. So superconducting qubits can come in many shapes and sizes, and they all have many different corresponding circuit diagrams. But for the rest of this lecture, I'll focus on one of the simplest and most widely used type of qubit, which is called the transmon qubit. A transmon qubit is basically just a Josephson junction shunted by a capacitor. And in these images, most of what you see here is what I'm going to call the capacitor. So in this paper, for example, the capacitance is between the two sets of interdigitated fingers, but there's also a capacitance ground plane. In this XMON design, the capacitance is really between the center-shaped X or plus sign and the ground plane. The Josephson junction is a submicron element. And so you can really see it best in SEM or AFM. And it consists of two superconducting electrodes with an insulating oxide between them. So because of these two very different length scales, we're going to approach the fab using a two-step process where we fabricate the capacitor pad and the ground plane if it exists, and that's going to be done using in a first step using optical lithography, and then we can fabricate the junction using electron beam lithography in the second step. There's also a way to fabricate both the capacitor and the junction in a single step using electron beam lithography, and I'll show you how that's done at the end of the lecture. But I personally found the two-step process to be more reliable and easier to do, even if it takes a little bit more time. Okay, so let's start with the capacitor fab. So the first step to any fab is choosing the right substrate and doing the right cleaning. So in the field, both silicon and sapphire are widely used, so you can use whatever is available to you. At Yale, for example, we use sapphire, but we're also looking into exploring silicon further. So for silicon, the type of silicon that you want is undoped intrinsic silicon with a high resistivity. And a thorough initial cleaning is usually a standard RCA clean, which is something that's widely used in the semiconductor industry. And it's a 3-part acid-base process where you first do an organic clean, then an HF dip to remove oxides, followed by an ionic clean to remove metal ions and other metallic contaminants. For sapphire, you want high quality sapphire. And there's several different grades of sapphire, and the EFG grade is the most common one. But recent work from our lab has shown that HEM grade sapphire can be even better. Now, if you have access to a furnace, you can also anneal your sapphire to make it lower loss. And in that case, EFG can be nearly as good as HEM after annealing. The annealing process is kind of like this extra sort of process that I'm not really going to go into in this lecture because it's not integral to the fabrication of a working superconducting qubit. But just know that there are other processes out there that can further improve the quality of your substrate. For the cleaning, you can also do an RCA clean for sapphire, but because there's no distinct amorphous surface oxide like there is in silicon, you don't really need to do the HF dip. And in fact, at Yale, we really just do a piranha clean to remove organic contaminants. I'll also say that if you don't want to do an acid-based clean, you can also just do a solvent-based clean, just using regular organic solvents like NMP, acetone, isopropanol. But it really seems that if you want to get the cleanest wafer possible, you should do these more aggressive acid-based cleans.
Okay, so before you move on from substrates, there are a few questions on that.
Sure.
So one is, why do you need high resistive silicon wafer?
Right. So generally, it seems to be the case that if you have that silicon with high conductivity or low resistivity ends up being lower loss. You want your substrate to be insulating, ideally, and that will lead to lower dielectric loss, especially in the cryogenic regime.
Yeah, and how high a temperature do you need for the sapphire to anneal it?
That depends. So when we do our annealing process, we go up to 1200 degrees. There's literature out there that only goes up to 1100 degrees. I've heard some people go up to 1400 degrees, but I think generally above 1100 degrees in an oxygen-rich environment.
So is there any references on this annealing process and like a documentation of what it does and what kind of a good effect does it do?
So there are several papers that talk about sapphire annealing for the purposes of surface reconstruction. To the point where if you do AFM on the surface of the sapphire, then before and after annealing, you can clearly see a difference where after annealing, you can observe monotomically flat surfaces and things like that. When it comes to what we care about, which is microwave quality and microwave losses, that work is still in preparation, but from our group, but we hope to have that out in the archive in a few weeks.
All right, cool. Yeah, I'll let you move on then.
All right. Okay, so now that you have a clean wafer, we can now deposit metal for the capacitor. So the choice of metal that you use can vary. So some groups use aluminum, other groups use niobium or tantalum. Some groups even use even more exotic materials like tantalum nitride or niobium nitride. The process can vary between all of these, but I'm going to focus mostly on a process based on niobium or tantalum. So there are two main ways to deposit, and those are evaporation and sputtering. In evaporation, you basically heat a source metal until it melts, where the vapor pressure becomes high, And in a vacuum chamber, that vapor can travel unimpeded towards the substrate and condenses, leading to an even coating of metal under wafer. And there are two main ways to heat that source metal. One is by conduction, and that's called thermal evaporation, where you directly heat the crucible using your using a heating coil. The other method is using an electron beam, which uses a beam of electrons that's focused by an external magnetic field to heat your source. So here, E-beam evaporation is generally seen as cleaner because you are localizing where you're applying heat, which leads to less heating of other parts of your chamber and less outgassing that can contaminate the quality of the film. One thing I want to note here is that evaporation is a directional deposition process. And because the atoms in the vapor have very long mean-free paths, because you're in a vacuum chamber, they travel in essentially straight lines. And as a result, it's easy to mask against deposition. And this fact will be very useful later when we do junction fab. The drawback of evaporation is that it's hard to evaporate refractory metals like niobium or tantalum because you need to put in so much energy that you'll start heating up the rest of the chamber. Which leads to outgassing that can degrade film quality. It can still be done, but you'll find that evaporated films tend to have lower TC than expected, or lower TC than if you had made those films using sputtering, which I'm going to talk about next. Despite that, depositing good quality aluminum films is really quite doable because aluminum has a much lower melting. It's much easier to evaporate. So the other method of metal deposition is sputtering. So in sputtering, you flush your chamber with inert gas like argon and ionize it, and then you apply a DC voltage to accelerate those ions towards your source metal, which we call a target. The ions will sputter off chunks of target metal with enough kinetic energy that they fly towards the wafer and deposit on it. And this is really the preferred method for depositing refractory metals like niobium and tantalum, because the energy required to sputter is sort of independent of the material's melting point. So you can achieve good deposition rates without heating the chamber. An important thing here is that for tantalum specifically, if you want to deposit alpha phase tantalum, you have to heat your substrate to at least 500 degrees. If you don't have that capability, you can also use a niobium seed layer. So you can deposit around 5 nanometers of niobium first on your wafer, and then you deposit your tantalum on top of that in order to force it to grow in the correct phase, even at room temperature. Yeah, so in contrast to evaporation, sputtering is not directional. Because the chamber is filled with argon, the mean free path is much smaller, and so within the path of the target to the wafer, the deposition is a bit more isotropic, which actually makes it almost impossible to do the type of junction fab that I'm going to go into in the second part of the talk using sputtering.
Just to interrupt with one quick question. So is aluminum not preferred to be deposited by sputtering? I think you just commented on you cannot do sputtering for the junction. How about for the capacitor? Yes, you can still, you can sputter aluminum totally fine for the capacitor. You can do that. Just making a junction using a sputtering process, at least in the more standard way, using double angle deposition, which I'm going to go into detail later on in the talk, is not really possible to do with sputtering, as far as I know. So people continue to follow up. So which gives better results, sputtering or evaporation for aluminum? I assume this is just for the capacitor. For the capacitor, that's a good question. I am actually not sure. At Yale, when we do aluminum-based processes, we almost entirely just do evaporation. And that's probably because the equipment that we have, because we can use the same deposition equipment that we use to make our Josephson junctions to just deposit aluminum as a capacitor layer, we just opt to use that.
whereas we use our sputter to deposit niobium and tantalum. And because we do these high temperature processes, we really don't want to deposit aluminum in a chamber that we're heating up to above 500 degrees. So we generally like to keep those processes separate. But I think I have heard of other groups that do sputter aluminum. The question about like which is better when it comes to aluminum, I'm really not sure. I don't know if there's been a systematic study that has looked at that.
Okay, another question: do long throw or other more directional sputtering variations provide enough benefit to match evaporation methods? Yeah, I'm not sure. Yeah. Do you know those techniques?
That I'm not sure. I'm not too familiar with those techniques, unfortunately.
All right. Yeah. Thanks.
But it's probably something worth exploring if it's possible to do directional deposition with sputtering. Give it a shot.
Yeah.
A lot of fab is just about, yeah, why don't you just try it and see what happens? Yeah.
All right. Let's move on.
Okay, so the other important question that often comes up is what should the film thickness be? So generally it seems that for niobium and tantalum, the film TC decreases with thickness. Once your film is thick enough, the TC starts to be close to the textbook value. But for aluminum, on the other hand, if you decrease the thickness of your film, the TC actually increases. And this, to my knowledge, is something that's pretty unique with aluminum, in that if you decrease the thickness or you do anything else that increases the film disorder, the TC ends up being higher. And granular aluminum, for example, is sort of an extreme form of this. But in general, reducing thickness increases disorder, which is in the case of tantalum and niobium. And it will also increase the kinetic inductance of your film and the magnetic penetration depth, which both also have the downstream effects of increasing conductor loss due to residual quasiparticles, or increasing conductor loss due to vortices. And it can also affect potentially quasi-particle dynamics themselves, such as the quasi-particle relaxation or the recombination rate, trapping rate, and things like that. To get around some of these potential issues, and to be honest, it's not really quite clear whether any of this actually matters. Even if your niobium TC is at 7 Kelvin, when you're operating at 20 millikelvin, that TC probably doesn't matter. But at Yale, almost standardly, we make our capacitor pads have thicknesses of greater than 100 nanometers. For example, our tantalum process uses a film thickness of 150 nanometers. Okay, so now that we've had our metal deposited, we can now do optical lithography to pattern the features. So we first coat the wafer with photoresist, which changes properties when exposed to light. And there are two types of photoresist. There's positive resist, where exposed areas become resistant to attack by a developer. And then there is negative resist, where your exposed areas become resistant to attack. So here's sort of a diagram to sort of show what happens. I have my wafer with metal deposited on it. I spin photoresist, and then I expose my pattern in certain areas using some sort of UV light. And if this resist layer was positive, the development removes the areas that have been exposed. And if my resist was negative, the development removes the areas that have not been exposed. So usually the developer that we use is in the form of a solvent or a weak base. For the resist that we use at Yale, our developer is TMAH, or tetramethyl ammonium hydroxide, that comes in a diluted form called MF319, which is really just a solution that's around 2.2% of TMAH. And then once we've developed, we can etch the unmasked metal away, leaving our desired pattern. Okay, So let's go over some of these steps in detail. Spinning photoresist is done. Yes.
Yeah, there's a couple questions from earlier on the deposition. So
Sure.
why do you use niobium seed layer for alpha tantalum, and what thickness of the seed layer is needed?
So if you want to grow alpha tantalum, there's a couple of ways to do it. One way is to deposit on a heated substrate. So generally, if you heat your substrate above 500 degrees and you deposit tantalum, it will grow spontaneously in the alpha phase. The other way, if you don't want to heat your substrate, or if you don't have the capability to do so, you can deposit a niobium seed layer, and that will, and if you just deposit around 5 to 10 nanometers of niobium first, and then deposit your tantalum on top of that, your tantalum will sort of be forced to grow in the alpha phase. And
yeah,
so
sorry,
yeah,
go ahead.
Go ahead.
Yeah, so can you use other material for seed layer? And also, if you were to use silicon as your substrate, would this process change?
I believe the seed layer works both on on sapphire and silicon. As far as other materials you can use, I know that niobium is one such material. I am not entirely sure what other materials. I wouldn't be surprised if there were other materials that you could use as a seed layer, but I'm honestly not sure.
Okay, yeah, obviously there are possibilities out there one can try.
Yeah. Like
okay,
I want to say that I've heard somewhere that tantalum nitride, but I can't recall a specific paper or source that says that you can do that.
Yeah, and on the lithography step, do you normally use UV tools with masks or direct laser writing?
Yeah, so I will go into that. You can use both, but yeah.
All right, thanks.
Okay. So yeah, so we spin photoresist using a spinner. It's basically has this vacuum chuck that holds your wafer and spins it at very high speeds. So you dispense some resist on your wafer, and then the spinner will spin. The rotational forces will cause that resist to distribute itself out and evenly coat your resist, or evenly coat your wafer. And the final spin speed will determine the thickness of your resist after you spin. One sort of recommendation I have is when you spin resist on larger wafers, like 4 inches or above, I recommend you do a 2-step spinning process where you do an initial slower spin in order to coat your wafer fully with resist. And then in the second step, you spin at the higher speed that's sort of going to be reflective of the final thickness that you want. So when it comes to the thickness of your resist, you have to be mindful of the etching process that you'll use, which we'll talk about in a few slides, because the etching process that you do might also attack the resist. So your resist needs to be thick enough such that the etching doesn't fully etch through your resist and attack the features on your pattern that you care about. So for example, for our processes, we usually spin around 3 microns of resist. And finally, we after spinning, we do a soft bake to evaporate the solvent and harden the resist before doing exposure. And typically for our process, we usually use S1800. So for example, I like to use S1827, which is actually not shown on the spin curve, but it would likely be a curve that's sort of right above S1822. And so we like to spin it around 3 microns thick. So now that we've coated our wafer with resist, we can now expose our pattern, and this can be done in 2 ways. Depends on the equipment that you have. So you can either do a direct write using a maskless aligner, where the machine will basically shine a beam of UV light onto your wafer and sort of traces around your desired pattern in order to selectively expose those regions. Or you can use a contact aligner and a photomask, which is basically a glass plate with the desired pattern on it. So here I've drawn the pattern on the mask using these black squares. And then you contact the mask onto your wafer, and then you shine your UV light through the mask in order to expose the regions that are not blocked by the pattern on the mask. And then once your exposure is done, you can develop your resist using a developer. So in our process, as mentioned earlier, we use the S1800 series, and from the data sheet, I can look up the exposure parameters and the developer compatibility. So our process ends up using a TMH developer, MF319, and we develop for around 1 minute, and that's enough to remove the regions of resist that have been exposed by the UV light. And then once our development is done and we're ready to etch, you want to do a hard bake at a higher temperature in order to increase the chemical resistance to the etch. So hard bake parameters can vary widely and can depend on the specific etching process that you use. Some hard bakes can be as high as 150 degrees Celsius or even more, while others can be a lot more mild at like 120 degrees for 1 minute, for example, which is what we do actually. But ultimately you have to figure out what gives the best results based off the equipment that you have, the processes that you use, and the parameters that you end up going. So here's an example of what a pattern can look like after exposure and development. So here I have a wafer coated with metal, and my photoresist is masking the capacitor pattern of my transbond. This is sort of the area where my junction goes. Okay. So now that we've done development, we can move on to etching. There are many different ways to etch metal. There's a wet etch, which uses an acid or base to chemically etch your unmasked metal. And here you want to use a photoresist that's resistant to attack by the etchant. For aluminum, you can use an etchant like MF312, which is 5% TMAH, or you can use aluminum etchant type A by Transene, which is a mixture of phosphoric and nitric acid. For niobium or tantalum, you can use tantalum etchant by Transene, which is a mix of HF and nitric acid. You can also do a dry etch using reactive ion etching, and this is actually what we do for our tantalum process and our niobium process. So for RIE, you're basically flowing a reactive gas and you're generating a plasma using an RF field, and then you're accelerating those reactive ions towards your wafer. And this allows both chemical and mechanical etching. Now, the exact recipes and parameters are very tool specific. But for example, if you want to etch aluminum using reactive ion etching, you want to use a recipe that's based off of some boron, trichloride, and chlorine gas. While for niobium and tantalum, you want to use a fluorine-based gas like SF6 or CF4, CHF3. And this is really where some process development is required, where you'll have to make some test pieces and vary the etch recipe by exploring the parameter space of gas pressure, flow, and power in order to change the etch rate and your sidewall profiles. And you want to characterize both the metal etch rate and the etch rate on your photoresist and make sure you're spinning a thick enough resist layer such that you can still protect the features that you care about. And of course, after you etch, you can remove the remaining photoresist with solvents like NMP, acetone, and isopropyl. And this is what your capacitor will look like after etching. So now you basically have your desired circuit pattern on your substrate, and now we're sort of ready to do the junction fab, which is going to really mostly be focused on this small area right here.
So a quick question. So when you do etching, whether there will be any change in the sample surface, like a tantalum or niobium, before and after etching?
Sorry, can you repeat the question? Was the question?
Yeah, so the question is about the impact of etching on the sample surface, on the surface quality, like the niobium and tantalum.
The impact of etching on the surface of the niobiums or tantalum specifically. Mm-hmm. So those areas will be masked by photoresist, right? So mm-hmm. you wouldn't really expect your etchant or your etcher to actually interact with that region, but the interface between the substrate and the vacuum, so this area, for example, can be affected by your etching process. So in particular, if you have, for example, too much, so for sapphire in particular, right? If you have too much of a mechanical etching in your RIE, so if your RIE powers are too high, for example, then your ions will have a lot of kinetic energy and can actually mechanically etch your substrate. For silicon, if you're doing a fluorine process, silicon is also vulnerable to fluorine-based processes. So if you're etching tantalum or niobium with SF6 or CF4, you will also attack the silicon as well. And so as a result, your silicon might also be partially etched and might end up being a little more rough as a consequence. And that can definitely affect the surface qualities of the substrate, the exposed substrate.
So there's also a question on the impact of your impact of strip on half metal on like niobium or tantalum. Yeah, it's actually not exactly clear to me what the question was, but I imagine the process of stripping away your resist, is it going to impact your metal surface quality?
Yes, it could. If you don't do a good enough job, it can definitely leave some residue. The nice thing about working with materials like niobium and tantalum is that they're highly chemically resistant. So you can do pretty aggressive cleaning after this stage and before you start your junction fab. So typically what we do for our tantalum processes is we just do a piranha clean. And a piranha clean is really good at removing all organic residues. So if we're worried that there's some photoresist left over or some hydrocarbons on any surfaces, then the piranha clean will take care of it.
Yeah, okay, there's endless questions. I'll run just one or two more. Yeah. So why tantalum and niobium is better etched with fluorine, not chlorine? And why is it the other way around for aluminum?
I believe niobium and tantalum can actually be etched with chlorine as well. Fluorine is just typically what we like to use. Fluorine-based processes can etch aluminum and its oxides, and sapphire is aluminum oxide. And given that we work on sapphire, we would rather use a fluorine-based process in order to eliminate any possibility of potential interaction of our etching with our substrate. The reason why aluminum doesn't interact with fluorine-based processes is I don't know the specific reason. It probably has something to do with the surface chemistry of aluminum. Yeah.
Okay, so last one. So you mentioned the hard bake resist step. So what is the hard baking protecting the device from?
So after development of your pattern, or after the development of your resist, you now have a photoresist mask that's masking your pattern against an etchant. That photoresist mask can also be vulnerable to your etching process. And in order to improve the chemical stability and the chemical resistance of that resist, you can hard bake the resist. And a true hard bake is something that's done at much higher temperatures, like above 150 degrees, where the polymers and the resist will actually cross-link with each other and essentially strengthen those interactions, making it very hard for that resist to degrade. But really, there's more of like a sliding scale where the higher temperature you hard bake at for longer periods of time, you will sort of strengthen the resist more and more. And so that's essentially why we do the hard bake. It's to improve the resist selectivity, the selectivity of the etchant to the resist.
Okay, cool. Yeah, lots of questions. Let's let you move on for now. Yeah.
Okay. Okay. So now that we have our capacitor, we can now make our junction. So let's talk about the junction fab. So a Josephson junction in general will consist of two superconducting electrodes separated by an insulating barrier. Nowadays in the field, this is almost universally realized using an aluminum oxide aluminum junction. Okay. It turns out that there is a nice relationship between the room temperature resistance or the normal state resistance across this junction and the Josephson inductance or the critical current. And it's given by the Ambigaukar-Baratov relation from this paper here. And so that basically says if you know the normal state resistance of the junction, then that's linearly related to the LJ. There's some dependence on the gap, the superconducting gap of the electrodes there. There's also a relationship between the room temperature or the room temperature resistance and the resistance just above TC. That's given from this paper, that combined with the AB relation basically gives you a sort of LJ or a resistance in kiloohms to LJ ratio that's around 1.25 nanohenries per kiloohm. Although in reality, this number can really vary from like 1 to 1.3, which is what I found in my experience. But it's sort of a good starting point for when you calibrate the process that you actually end up doing. This is a very process dependent quantity. It'll depend on the thickness of your films, the materials that you have, so the type of substrate that you use, whatever surface treatments you employ before deposition, and your oxidation parameters. The other thing is that, because resistance scales as 1 over the area of the junction, and the area over your junction for transmon qubits in the gigahertz range tends to be less than a micron, less than 0.1 micron squared. In order to pattern this thing accurately, you need electron beam lithography. You can't do this really optically. The other thing is that your Josephson junction properties are going to be very sensitive to tunnel barrier growth, and whatever contamination that can accumulate during the process of fabricating the junction. And so as a result, it's better that your Josephson junction should be made in a single step. So, and what I mean by that is you want to grow your bottom electrode, then you want to grow your oxide, then you want to grow your top electrode all at once without breaking vacuum. And this requires essentially a process that we call double angle evaporation, which I'll go further into in the next few slides. The other recommendation is to deposit thin layers of aluminum with high deposition rates. So 20 to 30 nanometers at 1 nanometer per second. That basically allows us to start and finish the deposition of a film very quickly in order to minimize additional film contamination due to the residual gases in your vacuum chamber. The thinner layers of aluminum also carries the added benefit of also increasing your TC. So For our process, for example, our bottom electrode is 20 nanometers thick, our top electrode is 30 nanometers thick, I believe a 30 nanometer thick aluminum layer has a TC of around 1.25 Kelvin. The 20 nanometer thick film has a TC around 1.35 Kelvin. And so the sort of average gap here is around 1.3, or the average TC is around 1.3 Kelvin. So we make our junctions using an additive process, and that basically involves deposition via shadow evaporation through a resist mask. And so the way that works is we have some resist here that we have developed a trench into, and then you deposit your aluminum. And aluminum will be deposited all on the surface of the resist and also in here. And then you do a process called liftoff, where you remove the resist and you're left with just the deposited aluminum on your wafer. Now, to make an actual junction, there are three main processes. They're called Dolan bridge, bridge free, and Manhattan. All three styles require an electron beam resist bilayer stack. So we have two types of resists. The more common one that we use is called PMMA, and a copolymer called MMA. So the PMMA here is the top layer, and the MMA is the bottom layer. And these are basically two electron beam resists that have different sensitivities to the electrons. So for example, PMMA requires a high dose to expose, and MMA requires a low dose to expose. And we can take advantage of that fact to make some interesting patterns here that I'm going to show you in future slides. The other thing is that although it's not shown in this cartoon here, single step this sort of junction fabrication process where we do double angle deposition, it involves some sort of angle deposition. So we have to tilt the wafer at specific angles to deposit in selectively exposed regions. So let's talk about the first type of process. It's called a Dolan bridge. And the approach here is to make a bridge using your resist and evaporate at two angles. And so in the simplest form, you're patterning this line and you make a bridge right here. And when you deposit at an angle, the bridge will block deposition in certain areas. And so as a result, if you deposit it at two different angles with an oxidation step in between, you can create a structure that's basically a Josephson junction. And of course, in order to do this, you need a bilayer resist where the area of the bridge is exposed with a low dose, and these channels are exposed with a much higher dose. The low dose will expose the MMA, which is under the bridge after development. The high dose will remove both the PMMA and the MMA. Okay, so here's sort of another, so what I'm going to do is I'm going to create a cross section that's sort of along this trench here. And that's what we're seeing here. So this is the bridge. And now we evaporate at two angles. So in the first angle, the deposition will be blocked by the bridge here, and so you'll have a gap right here. So the first deposition is yellow, and the second deposition is in green. So in the first round, you just have the yellow part, and then you oxidize, and that will create an oxide right here. And then you go in the second deposition in the opposite angle, and that will form this Josephson junction right here. Okay. And importantly, this for the Dolan bridge process is going to be dependent on certain parameters like the thickness of your resist. So and so you can basically do the geometry here, and you can determine what the length of this overlap region will be, and it's given by this expression, where WB is the width of the bridge, T sub M is the thickness of your. Actually, these labels are swapped. Tm is supposed to be the thickness of your MMA. TP is the thickness of your PMMA. I'll change that. Yeah. So this is how the entire circuit will look like now. So you can see that the capacitor pads have already been patterned here. We have our junction, which is really small, that I'll zoom into in the next slide and show. I also have a shorting strap here. Now, if you're making your transmons on sapphire, I recommend adding a shorting strap in order to prevent your junction from blowing up due to ESD. This can save your transmons if anything bad happens to them before you're finished fabrication. And if I zoom in to this region here, this is what the design will look like. So I have my junction leads here. I have the bridge right here, and so and the bridge here we will dose with a low dose, and the junction leads will expose with a high dose. And then over here we have these contact pads that will basically form the connection between the junction and your capacitor pads. Okay. And because you're doing an angled deposition, there's going to be a shift in the metal. So you also want a low dose exposure given in red in these regions right here, in order to provide room for that shift to take place, and to make sure that aluminum doesn't get deposited on the sidewalls of your resist. The other feature I want to note here is this notch shape that we patterned in our capacitor fab. This essentially serves as sort of like a universal contact geometry, such that no matter which angle you're depositing at, you will always deposit on a sidewall of your capacitor metal, right? So I am depositing here along this direction, and so that will ensure that I have deposition along the sidewall of my metal here and also here. But when I deposit along the other side, I will still have deposition along the sidewall here, and here and here. And this notch basically allows good electrical contact regardless of which orientation I'm depositing from.
So Suhas, maybe I missed this, but there's a related question. Would you have native oxide on the capacitor layer before making the junction? So what do you do to ensure they have metallic contact in the C shape you just mentioned?
Yes, so I will go over I'll go over the deposition process in a little bit more detail in the next few slides. But yes, in order to remove that oxide, you have to employ some sort of surface treatment, in particular an argon ion beam clean.
Okay.
Is
and you also just mentioned this shorting pad, and that is partially because you dice the wafer after the fabrication, right?
The shorting strap. So yeah, so dealing with ESD, we found to be a bit of like a stochastic issue. Like it can just happen randomly, and we won't really know why. It would usually be related to some unknown source of ESD that we generate at some point. So there was a time when I didn't have to use shorting straps at all, and my junctions were fine even after dicing. More recently, that hasn't been the case. And so we just found, in order to save ourselves the headache, we patterned the shorting strap. Basically, so, yeah. So
are you going to talk about the dicing step later?
Actually, no, I won't really be talking about the dicing step, because the dicing step is pretty straightforward. Yeah, it's and there's really no special precautions that we take I guess, except for, yes, what we found is that you are most vulnerable to ESD during dicing, and so you can argue that the inclusion of a shorting strap is specifically to protect yourself or to protect your junctions during the dicing process. But I do want to emphasize that you can accumulate ESD, or you can have ESD at sort of any step in your fab. And depending on how careful you are and how well grounded your equipment is, this can either be very effective or not really useful at all.
Okay.
One thing I also want to say is that from our experience and from our measurements, we haven't found any loss of coherence or degradation of coherence by adding the shorting strap. So we don't actually see any sort of penalty when it comes to additional losses by adding the shorting strap. So we just opt to put it in.
But you have to scrap them later on, right?
Yes, yes. Before you cool down your device, or when you want to probe your device, you do need to you do need to break this. That's right.
Okay, yeah, thanks.
Mm-hmm. Right. So this is sort of a diagram of what this pattern will look like. You have your contact pads here that will short your capacitor to your junction, that you'll dose with a sort of medium dose, I like to call it medium dose, around 600 to 900 microcoulombs per centimeter squared. You have your junction leads here that you'll dose with a very high dose, around 1400. And then you'll have your bridge that you dose with a very low dose, around 300. These numbers are going to be very dependent, again, on the type of substrate, the thickness of resist that you use, and also if you use an anti-charging layer or not, which I'll go into more in a few more slides. This is what the pattern will look like after development. You can see there's this exposed area, or this developed away area that corresponds to the contact between the tantalum capacitor pad and what will be the aluminum. Over here, you can see that there's a small area that's slightly discolored. If you can see closely, that's the bridge. That's the area where there's just a bridge of PMMA, and underneath it, there's nothing. And then after deposition and liftoff, this is sort of what the pattern will look like. You see, if you zoom in very closely in here, there's your Josephson junction. With this way of doing things, your junction width is going to be defined by the width of this lead. So if you want to change your junction critical current or your Josephson inductance, this is the only parameter that you'll have to modify. The junction length, so this overlap length here is going to be determined by the deposition angle, the resist thickness, and the bridge length, and that's basically this parameter right here. And importantly, there's really only 3 different doses here that need to be optimized. One sort of disadvantage to this approach is that larger area junctions are very hard to make, because if you want to make a large area junction, you have to make this bridge longer. If you make the bridge too long, then it can sort of collapse under its own weight. The other issue is that the total Josephson junction area, or the overlap here, is going to be sensitive to the thickness of your MMA layer. So if there are any variations in the thickness of your MMA from run to run, then your Josephson junction area is going to change as a result of it. So one thing that's sort of important to do as a result of these potential inconsistencies here is it's important to do a dose test in order to calibrate your parameters. So in a dose test, you make an array of junctions and pads in order to be able to probe them, and you vary the doses of specific regions along this array, And
Hey,
then,
Suhas,
yes.
sorry to interrupt. A very a clarification question. What do you mean by dose?
So dose is going to be the amount of charge or the amount of energy that you deposit with your electron beam during electron beam lithography.
Cool. And presumably you will talk about how to do oxidation, right?
Yes.
Okay. Yeah.
So yes, so you want to be able to do a dose test in order to calibrate how much actual doses you need. These are the doses that I use, but again, they're going to be very specific, or they can change depending on the choice of substrate and the thickness of resist and the type of basically all those parameters. So in order to calibrate that, you want to make a dose array where you vary the dose along each axis of the array. And then once you make all these junctions, you can probe them, and you can search for a range in which you have a stable, repeatable set of resistances. You'll find that in a proper dose array, you'll find that at the lowest dose, you won't have enough development at all, and you won't have a junction, which means you'll either probe short or an open. And at the highest dose, you'll be overexposed, and you will likely not have your bridge will have collapsed. You'll have a short, for example, and somewhere in the middle you'll have a range of parameters. So you'll have a range of devices in which you have stable resistances, and those are the doses that you should go with. And if there are inconsistencies on a run-to-run basis with respect to the thickness of resist that you spin, then this might be a dose array that you'll have to do more often than not. Okay, so that's the Dolan bridge process. The next process that I want to go over is the bridge free. So in the bridge free process, the approach is basically to make use of controlled asymmetric undercuts, such that one angle will deposit onto your substrate and the other deposition angle will deposit onto a sidewall. So basically the pattern kind of looks like this, where you have a fully exposed region right here, and then you have an artificial undercut here made by exposing this region with a very low dose, such that you only develop away the MMA here. And so as a result, when you do an angled deposition along this direction and this direction, you can create this overlap here, and you have these other thinner channels here with their own asymmetric undercuts, such that when you deposit in this angle, the lead to your junction is gonna deposit underneath this undercut, and same when you deposit at the other angle for this lead. So as a result, you'll have the wire that connects your juices and junction to the rest of your circuit is going to be deposited under this undercut. So importantly here, the reason this works is in these areas where you have your junction leads, one of the evaporations will actually deposit onto a sidewall here, and this sidewall ideally the sidewall will basically be a straight sidewall here, but you see that you also have a little bit here that's been developed away by a distance called delta min right here. This is what I like to call a natural undercut, and this basically occurs due to a proximity effect. And this proximity effect is basically due to either secondary electrons or scattered electrons during your e-beam writing, where your electrons can either scatter against your substrate, creating basically exposing regions of resist that are not they're sort of adjacent to your pattern, or by secondary electrons that are re-emitted by your substrate. And so as long as this delta min is small enough, then you should still be fine. You should still have deposition along your sidewall. But if this delta min is too large, then you can see that your exposure or your second evaporation might actually deposit on the substrate itself. And when you do that, you'll end up with a shorted junction. Okay, so let me show you what that looks like. So this is sort of the general CAD file. Here in the brown, I have fully exposed regions here corresponding to the wiring that leads up to my junctions. And in the yellow here, I have the very skinny leads that I've fully exposed. And here in this rectangle here, I have the artificial undercut that I'm inducing here using a low dose. Okay, and importantly here, there are two separate doses here. In the dark blue is going to be a low enough dose to expose the MMA without exposing the PMMA. But in the light blue here, because this light blue region is adjacent to the brown and the yellow region and the green region, which are all exposed with high doses, there's going to be some proximity effect. And so as a result, the additional exposure that's needed during the writing of these light blue regions needs to be slightly smaller. And so you can quickly see that because of these of large numbers of different doses here to keep track of, to actually do this correctly, you need to calibrate a larger number of doses here. And if you do it incorrectly, you'll end up with something that looks like this. So if you can see here, you see there's this region that's a little that's sort of shaded a little lighter color. This is actually a natural undercut that's formed by a proximity effect. Proximity effect basically due to this region being so large, and being because this region is so large, there's so many electrons here that has essentially been dosed by, that the proximity effect in this region is going to be very large. And so as a result, you end up having this natural undercut, which means that the value of delta min here is actually very large. And after deposition, you end up with a pattern that looks like this. And you have these additional traces here and here that would have normally you would want to have been deposited on the sidewall, but are now deposited on the substrate. And so as a result, your junction ends up being shorted. Now, this is a problem that can be fixed, but it's something that you have to be aware of. And really, one way to fix it here is to just make this region, this wide region here, you want to make it a lot thinner in order to reduce the total nearby exposure to your close by junction area. Okay, the last style that I want to talk about is the Manhattan style. So the Manhattan style is a seemingly very simple method. Basically, you pattern a cross that looks like this, and you deposit at an angle here, and then for your second deposition, you will rotate the wafer along the planar axis and deposit along this direction. And here again, you're using deposition on the sidewall to make an overlap. So in evaporation 1 right here, you coat this region with metal, but in here, in this region, you actually deposit along the sidewall of this resist. And so as a result, in the first deposition, you will only get a line here, and you won't get a line here. And in the second deposition, you will only get a line here, and you won't get a line here. So you'll end up with a pattern that looks like this. And so in between the first and second deposition, you have an oxidation step, and now you have a junction. And the nice thing about this is that the junction area is really only dependent on the width of these leads. And of course, if you want a larger junction area, you need a thicker resist in order to make this work. But as long as the natural undercut in these regions are small enough, you are less sensitive to proximity effects. Okay, so those are really quickly the three most common style of junctions. So let me walk you through a typical Josephson junction fab process. So this is after you've made your capacitor. So you have finished your RIE, you have removed the photoresist, and now you're ready to do your Josephson junction fab. So obviously the first step to do is to clean your wafer, make sure you've removed as many contaminants from your previous process as you can. If the capacitor metal is aluminum, you can really only use solvents or maybe oxygen plasma to remove any sort of residue. If your capacitor metal is like niobium or tantalum, you can be more aggressive and you can use a piranha clean followed by an HF or BOE dip in order to remove any excess oxides that may have formed due to whatever plasma treatments you employ. And then, so once you've done that, you can spin e-beam resist. Typically, what we do is we spin 700 nanometers of MMA, and then do a soft bake at 180 C for 5 minutes. For e-beam resist, these bakes are really due to essentially just due to completely dry out the resist. So when you pour resist, it's in a liquid form because it's your MMA that's suspended in a solution of some solvent, and then after baking it, you want to completely dry out that solvent and make your resist layer completely solid. And so you bake it at a very high temperature here for enough time to completely dry out the resist. And then you spin your 200 nanometers of PMMA on top, and then do another soft bake in order to dry that out. Now, if your substrate is sapphire, you want to deposit an anti-charging layer. And that's because when you're doing electron beam lithography, you're literally shooting electrons at your substrate. And if your substrate is non-conducting, like sapphire is, then the charge has nowhere to go. Those electrons have nowhere to go, and they'll build up on the surface and they will deflect, and they will scatter additional electrons that are being fired on the substrate. And so as a result, you need some sort of grounding layer so that those electrons have somewhere to go. And so typically what we use is aluminum or gold. So 15 nanometers of aluminum is enough, or you can deposit gold. You can do this either using a benchtop sputterer. So in our lab, we have a benchtop gold sputterer that we use to coat our wafers. We can also just deposit these using electron beam evaporation or thermal evaporation or whatever. Just know that if you do electron beam deposition because you're using an electron beam to melt your source metal, you could inadvertently produce secondary electrons that can partially expose your resist, which can change ultimately the required dose during your actual e-beam lithography. And this basically is just basically telling you that depending on what you use for your anti-charging layer, what thickness of anti-charging layer you use, can ultimately have an impact on the overall doses that you use for your junction patterning. If you're on silicon, because silicon is conducted at room temperature, you don't need to do an anti-charging layer. So, and then you just write your junction pattern with your EBPG. One thing is that because we already have an existing pattern on the wafer, we need to align our pattern with the existing pattern. And so this requires you to have alignment marks that you can see and align to in your EBPG, which you have to pattern during the capacitor fab. So usually these take the form of small squares. So for us, and of course, the exact type of alignment mark to use is going to be specific to what's programmed in your EBPG. So for us, our alignment marks are 20 micron by 20 micron squares that we have on the corners of our wafer that we locate in our EBPG, and we we perform an alignment sequence. So once you're done writing your pattern, again, if you're using a sapphire substrate, you need to remove your anti-charging layer. And if you have an aluminum anti-charging layer, you can use MF312. If you have a gold anti-charging layer, you can use potassium iodide. And then once you've removed that, you can just develop. And our developer of choice for PMMA, MMA bilayer is to use a 3-to-1 ratio of isopropanol and DI water that we chill to 6 degrees C and we develop for 2 minutes. Okay, so once we have done that junction patterning, we can now do our double angle deposition to deposit the junction. So the first thing you want to do is you want to try to do an in situ surface treatment. So you load your wafer into your evaporator, and hopefully your evaporator has either an argon ion mill or some sort of oxygen plasma capability. So these are the two types of treatments that are commonly used in our lab. Oxygen plasma for 30 seconds. It's designed to remove organic residue, and in particular for sapphire junctions, it prevents the aging of those junctions. Somewhere, somehow, if you do oxygen plasma on sapphire and you deposit your junction on top, that junction will not age. And by aging, I mean that there is a sort of after you make your junction, over time, if you keep measuring the resistance of your junction, you'll find the resistance keeps increasing until it just becomes open, and that's inherently due to the sort of metastability of the junction oxide and its interaction with the aluminum electrodes. But if you do an oxygen plasma treatment, that just stops happening. It will age for a little bit. The resistance will increase over a couple weeks, and then it'll stop aging. The other surface treatment is an argon ion beam clean. This is especially important if you're doing the sort of two-step transmon fab that I've been showing you, in which case you want to remove the oxide that is grown on your capacitor in that contact area where your junction pattern overlaps with your capacitor pattern. And argon ion beam clean of 30 seconds is enough to remove that oxide. At first, when we first tried this, we were worried that, because we're making junctions on sapphire and we're not doing oxygen plasma, that maybe our junctions would age again and age all the way to open. But it turns out that this argon ion beam clean also prevents the junctions from aging. So it's an added bonus there. So finally, then we can do our aluminum deposition. So we tilt the wafer by an angle theta. So for us, this value of theta is around 25 degrees. But again, it's going to depend on what thickness of resist you end up choosing and what sort of deposition angles that you end up choosing, which will determine what this overlap area is going to be. And so the first aluminum deposition goes like this. We deposit 20 nanometers at 1 nanometer per second. And then after that deposition is done, we do a static oxidation where without breaking vacuum, we introduce oxygen into the system, or into the chamber. We pressurize up to around 30 torr, and we just wait for 10 minutes. And this is what we call static oxidation. So we just pump the whole chamber full of oxygen, and we just let the system oxidize, or we let the aluminum oxidize on its own. The nice thing about aluminum is that the oxidation is self-terminating, which means that it will sort of grow to around 2 nanometers, and then basically the thicker the oxide grows, the slower the growth becomes. And so most of the time, if you just leave this in here forever, the oxidation, the oxide will grow to around 3 nanometers, and it'll basically just stop. For our junctions, when we do 30 tours for 10 minutes, when we look at this junction under a TEM, we can actually measure the thickness of the oxide and find that it's around 2 nanometers. But of course, it's important to note that different oxidation pressures and times will lead to different critical current densities. So, if you increase the pressure and you oxidize for a longer period of time, you could grow a slightly thicker oxide. It's not linear though, but if you grow a slightly thicker oxide, you will have a different critical current density. And so it's important when you make your junctions or when you develop your junction fab, is that if you have a standard process, this step needs to be fixed and sort of standardized in order to ensure that you have the same critical current density every time. And then once the oxidation step is done, you pump out all the oxygen, and then you do your second aluminum deposition. And here we tilt the wafer in the opposite angle, and then we deposit 30 nanometers at one nanometer per second. The second aluminum deposition is going to be thicker than the first because we want to basically have enough aluminum such that we can basically coat this sort of step up like this without breaking the aluminum. You can imagine that if this first layer is too thick and the second layer is too thin, you will have some trouble evenly coating the sidewall here. And finally, after deposition, you perform liftoff, remove the remaining photoresist and all the remove the remaining electron beam resist and all the metal that's deposited on the electron beam resist. And with this, we usually lift off using NMP, heat it up to around 80 to 90 degrees, followed by a rinse in acetone and IPA.
All right, let's run a full round of questions. There are a lot of questions accumulated. Let me pull that out. So first of all, what does EBPG stand for in your previous slide?
Oh, it stands for electron beam.
Pattern generator or something, but it's not important. It's the model of your tool. So maybe you just clarify.
It's yes, it's the model of the tool. It's by Wraith EBPG 5200. I believe it's electron beam pattern generator.
Yeah, it's an electron beam lithography tool, and you can use any tool. It doesn't have to be the CBPG. Okay, so just to clarify on your anti-charging layer, do you deposit gold or aluminum on the resist or on the substrate?
On the resist. Yeah. So the correct order is you spin your MMA, then you spin your PMMA, and then you deposit your anti-charging layer on top.
Yeah, then there's a question about like the property, the quality of the resist over time. So in your experience, like how much does the expiration date matters, and how much does the storage condition of the resist, say the temperature of the clean room matter? Like what do they do over time, and do you like rigorously follow expiration date, for example?
Yeah, great question. So we don't rigorously follow expiration dates. Basically, what we have is we buy like a big bottle, like a quart of resist, and we store that. And then for the specific resist that we use, we pour it into smaller bottles, and we take resist from those bottles and we dispense it onto our wafer. And so that's basically done to minimize the amount of times that you open your main bottle, your stock. Basically, whenever you expose that bottle, or whenever you open that bottle, you're basically exposing your resist to atmosphere, so that resist can dry out over time. And if it dries out over time, you will alter your spinning properties, right? So when your resist dries out, it becomes thicker, which means that if you spin your resist at the same speed, you will eventually spin a thicker layer of resist than what you wanted. And for a process like the Dolan bridge, that's going to definitely affect your junction area. But as long as you maintain your bottle of resist well and make sure that it doesn't dry out, it can last well beyond its expiration date. As far as the temperature, humidity, environmental conditions, they all matter, which is why we store our resist bottles in the clean room, which has a well-controlled temperature and humidity at all times. Yeah, I would imagine that for e-beam resist in particular, like you don't want them to come into contact with water or moisture, because that can ruin the exposure properties and development properties. So you want to make sure that the humidity that it's exposed to is well controlled.
All right, so another question on NMP. What is it? What's NMP? And is there a reason for using NMP over, say, acetone for liftoff?
NMP is a degreaser. It stands for N-methylpyrrolidine. Really known, I think. It's a degreaser. It's kind of like it's kind of like a soapy consistency. It's very hydrophobic, if I remember correctly. And so we use that as sort of like an initial cleaning step. So whenever we do what we call a solvent clean, we start off with NMP, and then we follow it up with acetone and then IPA. We like to use NMP for liftoff because acetone, I believe, has a very low flash point, so you can't heat up acetone too hot. But NMP has a much higher flash point, and so we can heat up NMP to around 80 degrees safely. And at higher temperatures, it's more active and can dissolve the resist a lot easier.
Cool. So another couple questions on oxidation. So is the oxidation done in a load lock or in the actual main chamber of the deposition system?
So that's going to highly depend on your specific system. In our lab, we have a 3-chamber deposition system. So we have a load lock, and then we have a deposition chamber, and then we have an oxidation chamber. So actually we do our deposition in our deposition chamber, and then we transfer it to an oxidation chamber where we do the oxidation, and then we transfer it back into the deposition chamber for the second layer of deposition, and then we move it back to the load lock for unloading. There are other systems that don't have this, that only have a load lock and a deposition chamber, in which case, you know, or they just have one chamber, in which case you can still do it. You would just introduce your oxygen in that same chamber.
So why do you use static oxidation over plasma oxidation?
Great question. The most blunt answer I can give is because that's what works.
Awesome.
And there hasn't been, so the thing about these junctions, you know, there's a reason why everyone uses aluminum oxide, aluminum junctions. There's a reason why everyone does static oxidation. It's because that is sort of the tried and true method for the past 15 years now, I think. It's what's always consistently produced good quality junctions. There's definitely a parameter space to explore. In fact, I believe the original grant that from our lab that actually got us our deposition system also included sort of proposals to experiment with different oxidation systems, with sort of different oxidation recipes and processes, which involve, you know, things like plasma. But I don't think it's been adequately explored.
Okay, so a question on aging. So what's your like a typical aging parameters? How much does the resistance increase in the first few weeks? And also, do you see qubit coherence time also change when the junction ages?
So I'll answer that second question first. When your junction ages, your resistance will usually increase, which means your LJ will decrease, which means your frequency will decrease, which means your for a fixed sort of internal Q, your T1 will increase, right? But other than that, in terms of with regards to intrinsic loss, we haven't really noticed that it changes by a lot. Only just because the frequency changes, the T1 will change. As opposed to address the question of how much do we age? Let me think. Personally, with the junctions that I've made, I haven't noticed a lot of aging. The most aging I've seen is after like 9 months, the resistance is increased by 1 kilo ohm. But within like a week, that's like 10%. Okay. Maybe no, like 15%. But like within a week, I haven't noticed any sort of aging within 1 week. But it's not something I've systematically looked at. I know it has been systematically looked at in our group in the past, but I can't recall off the top of my head how much that aging is. This is with the argon, with the argon ion being clean, by the way, on sapphire.
I see. Cool. Yeah, we'll let you move on. Yeah.
So that was the two-step transmon fabrication process. This is the last slide, by the way. So there is there's also the single-step process. So you can make your capacitor and your junctions all in one step using electron beam lithography. And in essence, this is basically the same process as the Josephson junction fab process that we've gone over in the past few slides. The only difference is you pattern the capacitor pads as well as the Josephson junction. The advantage of this is that you only need one deposition step and one liftoff process. So the whole fab process can be extremely quick. One issue is that the large, because you're writing very large regions here, it might lead to excess proximity effects, and so you have to account for that. And so one way to account for that is to pattern very skinny leads going up to your junction. And as long as, and that will sort of minimize the overall dose deposited to the wafer in this region that's 50 microns away from the junction. So the process ends up being pretty straightforward. You use a lower dose for the capacitor pad, around 600 to 900 microcoulombs per square centimeter, which of course depends on resist thickness, the type of anti-charging layer you use, and the substrate that you use. In my experience, I usually opt not to make transmons this way because they tend to be more lossy. Sorry, this is a typo. They tend to be more lossy and also less consistent. Because you have this very large writing area, you can oftentimes accumulate artifacts during the writing, which can lead to things like weird development patterns. You can sometimes find areas that don't develop at all, or you'll find resist peeling off during development, which can ruin your entire pattern. But sometimes, like in this case, it works and it can work perfectly. But a lot of times it doesn't. In my experience, doing the two-step fabrication process, even though it's longer, it ends up being more reliable and more consistent. Yeah, I guess that's it for this lecture. I wrote down a few, I guess, homework exercises. These are really, there's really only one main, I guess, homework assignment, and that is to make your own transmon qubit. and I've written down a few things that I think are sort of necessary steps to take in order to have a well-calibrated process and a process that you understand and know that you can reproduce in a viable way. Yeah, thanks for your time, and I will take any questions you may have.
All right, we already have 43 questions answered and counting,
Right.
but people, you're welcome to type in more. So maybe I'll just start with this question. How much time takes on average to go through the process you're describing today, from the beginning to the end to fab a transmon?
It would depend on the process. So if you're doing this, I can imagine this a single step fab process. I can imagine you can do it in 2 days if you spend all of your time on it. For the two-step process, I would say a week. If you spend all your time, you can do it in a week. Yeah.
Does the 2 day or 2 days or a week include like a testing, like those testing, or is it like when you have a working recipe and you just go ahead and do it?
That's when you have a working recipe and you just go with it. Yes. Yeah.
Okay.
Oftentimes, like when I want to make these devices, so for us, we can make multiple devices on one wafer, and oftentimes we can just incorporate our dose testing or dose arrays on the same wafer. So for example, if I only need one working device on a 4-inch wafer, I can make 15, 20 devices and use different and pattern each one with a different junction area. And I just pick the one that works and we go with it. So in that case, I only need to do this once in order to get a working device.
Okay.
Now, that being said, for a grad student, we oftentimes have multiple things going on at the same time. Like maybe we have some lectures to go to, or some group meetings, or some presentations we have to prepare. So it can oftentimes take longer than a week or 2 days. But I'm saying if you truly have 5 full consecutive days with no interruptions, you can definitely get it done.
Okay. And let me just check on the questions a little bit. Do you follow any special techniques like precautions when wire bonding the JJ devices?
Wire bonding. So in our lab, we usually we make 3D transmons. So those are floating transmons without a ground plane. So we don't actually do any wire bonding. But there are others in our group that do wire bondings for, say, parametric amplifiers and stuff like that. And I believe the big precaution that you take is make sure you have one of those ESD bracelets, and make sure that you yourself are grounded and you're not generating any excess electrostatic discharge.
And this one,
and make sure your bonder is grounded as well.
Mm-hmm.
Yeah.
Yeah, this one I didn't especially hear you talking about. The question is, I've heard the conducting layer that you have to spin can be expensive. Are there more widely used, cheaper alternatives for conducting layers?
Yes, so I didn't talk about conducting layers. I talked about anti-charging layers. So there is another alternative, I guess, to depositing a separate anti-charging layer, and that's by spinning a conductive layer. So I think one common one is called PSSA, which is a water-soluble conducting layer that you can just spin on top of your e-beam resist stack in order to have that sort of anti-charging layer. I have had some colleagues try it, and they said it has worked. But yes, it is expensive, and the alternative, of course, is to just sputter on your own anti-charging layer, like using gold or aluminum. Or yeah.
All right, I'll give you one last question. What are the current challenges for qubit fabrication? You have shown established processes which works well. So if everything is in your control, what area in fabrication would you like to improve?
Great question. I think obviously you want to improve everything, because everything can be better. We're not perfect yet. Well, yet I don't think we'll ever be perfect, but you know, there's all the, like, you can improve in every area in order to minimize additional losses due to your various interfaces or due to various materials that you use. One of the things that I've seen that are particularly annoying has to deal with the junction properties themselves. So ESD, for example, is one thing that can really be a pain, especially, you know, after you spend a whole week fabricating a device and you find that it suddenly just shorts or blows up right at the very last step due to ESD. So I would say that's definitely a challenge. Another challenge is, of course, reproducibility of junction critical currents and uniformity, especially on a single wafer. So, you know, you'll definitely find that even on the same wafer, if I write two junctions using the exact same parameters, you can find that actually just due to their locations on the wafer, they can have noticeably different resistances, and hence you know, critical currents.
Okay, so that's the end of today's lecture now. So you're hearing a silent round of applause right now. So thank you, Suhas, for joining us today. And also like to thank the 77 attendees who stick to the end of this lecture. So just a reminder, Monday is the day before July 4th. We're going to skip that day. And the next lecture is going to be next Wednesday on July the 5th is going to be the next lecture. And you guys are going to see Suhas again. So next lecture is going to be Suhas together with Miguel from MIT. The two will in tandem and talk about the device packaging for both planar and 3D qubits. So please tune in on Wednesday, July the 5th to join us on the next class. All right, yeah, see you guys next week.